So let's talk a little bit about the difference between physics-based or physics-driven and data-driven modeling. So on the left side here, you'll see I have that same analytical equation repeated. And so this would be an example, again, of a physics-based model or a physics-based equation. So what I've done is I've developed an equation to simulate a physical process. But what I've also done is I've put in some simplifications in order to make that, that equation not only, I guess, accomplishable or solvable in the sense of I need to have variables that I could actually measure or actually quantify. And additionally, what I've done is especially because I've made this a linear equation, I think that we all understand that the physics of Earth don't generally occur in linear ways, right? Physical processes tend to be described by higher dimensional equations, and yet we can usually approximate those processes using linear equations, which actually makes them more computationally efficient to solve. And by that I mean that it's much faster to process a linear equation through a computer than it is a higher order equation. And so, you know, what happens when you do that, and I'm not saying that this is a bad way to go. I think a lot of people have had enormous success doing physics-based models with linear or linearized equations. You know, one of the problems with that, though, is that there's an inherent addition of user bias and model bias, right? So, and there's a couple of different sources there. One is that I, as a scientist, wrote this equation. So I have already introduced my personal bias by determining, based on my expert knowledge, which is likely imperfect and incomplete and different from other, you know, quote-unquote experts. I'm not really an expert, but I'm just saying.
You're so modest.
Yeah.
I like it.
But anyway, so I'm saying that I have created this equation using my expert knowledge. Somebody else probably would have created a different equation, right? And this equation likely, and I can tell you in the case of soil moisture, right, most certainly does not fully encompass the variability of this true physical process, right? I'm never, with this equation, truly going to be able to predict soil moisture 100% accurately. And so, because of that, a physics-based model actually needs to go through what's called a calibration and validation process. And so what you do during the process of calibration and validation, we talked, I think, maybe just a little bit about this earlier. If you're familiar with Bayesian inversion, that would be a very classical approach to calibration. What you're doing when you're calibrating a physics-based model is you are taking your set of inputs, you're making some type of prediction, likely using some type of analytic equation, like I have here. And then you are comparing your, what you do at the end there is you compare your predictions to some known or true data that we call calibration data. And so really it's a very similar process that we're working through with these neural networks, right, where we're always comparing our predictions to true data. The advantage of using the neural network is that once you have the trained network, you no longer need to have that observational or true data, right? The disadvantage of a physics-based model in that sense is that, especially geospatially, we don't often have access to calibration data sets or observed data sets that are spatially continuous, especially, or that you may not have very long temporal records, depending on which dimension is maybe the most important for your prediction of interest, right? So that's a limiting factor of a physics-based model, in that for whichever area of interest you are running this model over, you know, you really need to be able to have calibration data sets in order to be able to make accurate predictions. You know, there's a saying that gets tossed around in modeling communities, which I think is attributed to a statistician named Dr. Boxbeck, could be completely wrong. But the phrase is, you know, all models are wrong, it's just that some are less wrong, is essentially the gist of it, right? And, you know, that's maybe a little dramatic, but really what we're saying is that we're always trying to make the best prediction that we can possibly make. And you have no chance of doing that if you have an uncalibrated model. That's really the point that I'm trying to drive home. So,
I've heard it is all models are wrong, some of them are useful.
all models are wrong, some of them are useful. And what's the source of that?
Do you know who said that?
Some hydro guy.
Some
Yeah, it was
hydro
a
guy,
yeah,
okay.
hydro guy.
We'll
Well, I thought
cite
it might
some
not be
hydro
fine.
guy for that phrase, thank you. Anyway, so I think we've covered physics-based modeling, at least, you know, as an overview pretty well. So let's talk about data-driven models now. So again, you know, we talked about this a lot today. What we're really doing with data-driven models is we're showing the computer a series of cause and effect relationships that would represent the inputs and outputs of that analytical equation, right? And really what we can do is if we have a, you know, an analytical equation that we can run through a physics-based model, we can actually create what's called a surrogate model by running that model hundreds of thousands of times and then taking the inputs and outputs and calling that our cause and effect relationship, really, right? So, you know, maybe the downside there is that if the data that you're using is maybe not particularly accurate, then you're only going to be able to make predictions that are as accurate as the data that you feed in to the model, so to the deep learning model. And so because we don't do that secondary calibration step, it's really more of an internal calibration as we're going through the backpropagation process. So one of the nice things about this, though, is that let's assume that we're using very accurate data, our target data or our Y data is very, very accurate. Then one of the wonderful things is that you know, in uncovering that mapping from X to Y, what we're really doing is we're uncovering physical relationships that couldn't be measured or approximated, that we would never be able to create an analytical equation that would fully encompass a physical process. We can approximate fully encompassing a physical process by determining these physical relationships via that mapping. So remember when we were talking about the number of parameters that you're generating or that you're trying to solve for when you're doing these neural networks. So when I'm talking about the number of parameters, in a way, if you were to think of those parameters as parameters or inputs into an analytical equation, you know, we're talking about hundreds of thousands or millions of parameters describing the variability of a physical process. And that's quite a few more parameters than I have over here on my physics-based side. And it's also quite a few more parameters than I could ever hope to physically measure, right? Especially when we're talking about geospatial data. And so that's a really great advantage. But of course there are some sources of error, and we've mentioned some of these so far. I think that, you know, the trained model is only going to be as accurate as the data that was used for training. And we're not able to, this is called transfer learning. It's very difficult to predict scenarios that occur outside of the system state represented by the training data. And so what I mean by that, so let's think about, I mentioned surrogate modeling a little while ago. So or maybe we don't even need to worry about surrogates, but let's assume that we have a very well-trained data-driven model or a deep learning model that is predicting soil moisture within a particular watershed. And the data that I've used to feed in are going to be the weather data and some initial condition data. So what the land use was like at a particular area, slope, soil type, all those types of parameters are going to be really important, right? So let's say that between the time I collected my data that I used to train my deep learning model and 10 years from now, the system state has changed dramatically, right? There has been a mean shift in the environmental conditions, meaning either, let's say, we used to receive 800 millimeters of precipitation and all of a sudden we're receiving 1,400 millimeters of precipitation a year, you know, or let's say that the land use has dramatically changed from agricultural land into now urbanized land. Urbanized land is going to have a much higher runoff percentage, right, of the incoming precipitation, so that's going to affect our soil moisture flux considerably. And so if there were a shift in the mean state conditions or the environmental conditions of a particular area that you had a neural network trained on, that neural network is no longer going to be able to make accurate predictions, and you would have to retrain that network. But, you know, I would assume that within, you know, a 10-year period, hopefully, well, I mean, climate change is a real thing, right? Maybe we're going to have some more intensified changes than we think, but.
Is it?
Sorry?
I was going to comment. So I review proposals for DOE on some of the grants that are submitted. And one of the things that I always look for when I'm looking for these sort of proposals for real-world applications in geosciences is a combination of physics-based modeling and some sort of artificial intelligence via machine learning or deep learning, etc., right? Anytime you just have one or the other, it's usually problematic and it's going to be highly limited. And then the foundation for all that is that you have a truly rich data set, because you really can't do good deep learning without it. So if that pyramid of 3 things is not there, proposals are just highly suspect.
Yeah, so the, just for the recording, the comment was that, often what reviewers look for when they're looking for some type of modeling work is a combination of physics-based modeling, data-driven modeling, and a very robust data set. And I would say those are probably 3 great, foundational pillars when you're thinking about moving into any type of modeling, really. But I think, especially because we have such a wealth of, especially in the United States, we have such a wealth of data, right? You can go online to USGS and pull up just publicly available data that goes back to the 1800s, and it's a wealth of data there. We have, more data is being created in one day now than was being created in the first 10 years of the internet, right? So we have, remote sensing data that is globally distributed, and I'll talk a little bit about that. But we have these large data sources that are just ripe for the pickings to be able to do these deep learning applications. So, if you're doing any type of modeling, I think it's a wonderful thing to be able to take advantage of to even just enhance your physics-based modeling. And okay. So that's a little bit of an overview between the, some of the primary differences between physics-based and data-driven modeling. Some of the advantages, again, that I want to kind of drive home with data-driven modeling is that once you have a trained model, it's very computationally cheap to be able to run, and it takes off the, obligation of the user to have calibration data, right? All the user needs is the input data, and they should be able to make very accurate predictions. So in terms of, just a general usage, I think that it might be easier for the average user to be able to employ a pre-trained data-driven model than it would be to employ a pre-trained or a physics-based model that they then need to employ a secondary calibration step with. Has anybody had an experience trying to do this of employing a model that you didn't write? Has anybody struggled with that?
Anyone who has an advisor.
Yeah. So the response was anyone who has an advisor, and that's, I think, quite true.
And it's usually in Fortran.
And it's
always.
It's always in Fortran.
That's true, right?
Yeah, SWAT is written in Fortran, and of course I have some SWAT developers who are likely going to watch these videos, so I love working in Fortran. So going back to my own research goals, I kind of want to talk about this in a big picture kind of way. So why is it even important to predict soil moisture, right? Who cares about how much water is in the ground? Actually, everyone, right? So one of the reasons that we're really interested in soil moisture is that we consider it a key hydrologic metric for subsurface and particularly near surface water flux. And this is extraordinarily important when we think about things like risk analyses for flooding or for crop viability, right? If the amount of water in our near surface environment becomes too much, if it becomes saturated, we're going to have floods. If we don't have enough water in our near surface environment, we're going to have droughts and then maybe not be able to produce enough food. So these are really, really big issues that we actually need to be able to predict in near or real time. And so, really what we're looking for here is to be able to build a computationally efficient, lightweight, and yet very accurate tool to analyze data and predict soil moisture, this key metric, in real time, or hopefully real time, depending on what forecast we have access to, right? And really we're thinking about this as an application for potential or risk analyses, but there are a number of applications that I'm sure could be marketable. So my research objective, again, and I'll just reiterate, is what I'm doing is I'm taking this, I'll talk a little bit about it, but I'm really just trying to estimate soil moisture on a high resolution grid. So I'm geospatially speaking, right? I'm looking at a 10-kilometer grid. I'm trying to accurately predict soil moisture along this grid, given a set of inputs. So what I'm actually going to be using is I'm creating, still kind of coming up with the terminology for how I want to talk about this, but I guess I would say kind of a pseudo-surrogate model in a way, right, for this SWOT model. So the reason I say pseudo-surrogate model, well, let me talk about SWOT just a little bit. So SWOT's going to take a series of both static and dynamic inputs. So let me back up a little bit. The static inputs are going to be the soil type, land use, and the type of topography or slope that we expect at each of those grid cells. So I talked about that 10-kilometer grid. I have input data from SWOT that's distributed along that 10-kilometer grid, right? And that's going to set the initial conditions for each model run, or what we would sort of expect the mean state of the system to sort of look like, right? Or the bounds on that system. And then we're also going to feed in dynamic weather inputs. So this is how the system, these are the drivers that are going to lead to changes, or the causes that are going to lead to dynamic effects at each time step of the model. And what we're going to be predicting is, with SWOT predicts both water flux and biomatter flux. In this case, what I'm really interested in is the water flux in the near surface environment. So again, what SWOT, this physics-based model, is doing is taking these inputs for weather parameters, which is our dynamic data, and static parameters for water flux and biomass, running that through a physics-based model, and predicting soil moisture. SWOT actually predicts a lot of different values. The one I'm interested in is soil moisture, right? So it's a physically based model. It runs daily on a global grid. I'm actually only using a subsection of the US grid, start small and get more complicated, right? Yeah, there are a couple things that we're looking to actually work on with the model, which would be to improve some of the modules that for nutrient cycling, but I'll talk about that later. So what I'm doing is I'm trying to create, this was my initial idea, was to create a deep learning surrogate for SWOT, right? So what I thought, well, let's take all of those SWOT inputs and pass that through a deep learning model as opposed to a physics-based model and try to predict this soil moisture. Well, you'll see I have this term remotely sensed here, right? So the reason that I called this a pseudo-surrogate model is that, so SWOT actually, for me, in at least the area I was using it in, I wasn't having a lot of success in accurately predicting soil moisture. Remember, this is an uncalibrated model that I'm working with. So I did try to do some calibration with it, but you know, one thing with when you're doing calibration is that the model needs to be structured so that there are a sufficient number of adjustable parameters to which your prediction of interest is sensitive to. So in my input data set, I need a sufficient number of parameters that I can adjust to create changes in my prediction of interest, right? If I have a prediction of interest that isn't necessarily sensitive to most of my input parameters, then I have fewer chances or adjustments that I can make to try and calibrate or move my prediction of interest more towards what I know the value should be. So the difficulty that I had with SWOT, and I should specify that I'm working with some collaborators at the USDA on a beta version of SWOT. So my comments now don't really have much to do with the full version of SWOT for more experienced users. But you know, with this beta version, what I found was that my prediction of interest, soil moisture, did not have sufficient sensitivity to enough input parameters to make the Bayesian inversion process effective. And so to do a true surrogate model, I would actually need to have a calibrated SWOT model to be able to run hundreds of thousands of times and generate the input and output data for, and then use that as my input and output for my neural network, right? That was the original idea. However, the calibration didn't work out. So we thought, well, let's look at this another way. We have this globally gridded data set on a fine, you know, relatively fine resolution, 10 kilometers. That's this input data for SWOT. And that's a wonderful wealth of training data, right? Who can turn that down? That's really, you know, when you think about geospatial data, it's very uncommon to have a continuously gridded data set. And so that's a wonderful wealth of data that we wanted to be able to leverage. But I'm actually not running the SWOT model at all, right? I'm not using the SWOT predictions in my mapping process. What I'm actually doing is I'm taking these SWOT inputs and I'm mapping them to satellite data. So soil moisture that was actually measured from a satellite which I'm considering observational data. So that's why I call it a pseudo-surrogate model, because I'm not actually using the model, I'm just leveraging the, basically the wonderful work that a lot of SWOT developers did to compile these data sets, right? So some of the advantages here is that I'm actually able to accelerate soil moisture forecasting. So my trained model, even if I were using SWOT, right, my trained deep learning model actually runs faster than SWOT does, right, the physics-based model. So that's kind of a nice thing that we tested out. But in doing this, we have to remember that we need a large volume of samples, and of course the initial thought was to run SWOT many thousands of times, and instead what I've done is I've just chosen many thousands of data points, like initial data points on the grid, right, and I'm using that as my training data set. So just a little bit of information about some of the satellite data that I used. I think we'll maybe talk more about this on the next slide, but one thing to notice is that for this, so SMAP is a NASA satellite, it's soil moisture active passive, and this is obviously a satellite that is measuring soil moisture. This is the one that I'm using to create my target data, or my training data targets, right, during my neural network process. One thing to notice is that the spatial resolution is quite a bit larger than the grid cells that I talked about with the SWOT data. And so at the end of my sort of predictive, at the end of training this model and making my predictions, I actually still need to downscale that data. So that's an important thing to think about when you're working with spatial data, is finding ways to work with data of different resolutions, right? And we can still do that with these neural network approaches. So in order to do this, remember I said that I have a globally gridded data set. Well, there's a lot of variation in a global data set, right? And whenever you're doing a modeling task, I think it's best to start as simply as possible to remove the amount of, what's a good way to put this? I guess to remove the amount, the number of variables that you have to monitor. So if you make a small change and you see a number of effects, it's difficult to attribute a specific effect to a specific change unless you have a relatively simple framework that you understand very, very well. That's why working with that simple model of doing a mapping between y equals x squared is really nice, because I understand the behavior of that model intuitively. And so if I make changes in my deep learning process, I'm able to identify what the causes of those changes were. So similarly, I wanted to choose kind of a homogeneous test bed to be able to work with this deep learning model. And so what I did was I'm running this pseudo-surrogate over a small watershed in northern Alabama and southern Tennessee that is, the river that runs through it is the Middle Tennessee Elk River watershed. And the reason that I chose this is that when you're remotely sensing a quantity, it's best to do that over a relatively homogeneous surface. So in terms of soil moisture, what's going to be really important, or in homogenization of this watershed, it's important that it's relatively flat. So here you can see an elevation profile of the watershed going from east to west. And also, the vegetation is relatively homogeneous. And that's really important here. We have largely pastures and deciduous forests, which agricultural lands are actually going to be the easiest to do remote sensing over, because they're they're highly gridded, which I guess is nice, but they tend to be, all the same plant, all relatively the same height, and that's a very even surface to be taking measurements across or over. The reason that it's really important to have a homogeneous surface is that when you're remotely sensing a quantity, so I'm trying to remotely sense soil moisture, I'm not actually directly measuring soil moisture. What I'm directly measuring is a quantity called brightness temperature that I then pass through what's called a soil moisture algorithm in order to get my soil moisture out. So I'm back solving really for soil moisture. But this initial brightness temperature is actually a bulk measurement of brightness temperature associated with the soil moisture, the atmosphere, and vegetation. And so what I need to do in the soil moisture retrieval algorithm is I need to be able to create those different partitions so I understand the amount of that bulk that bulk brightness temperature measurement that I can attribute to soil moisture so that I can accurately backtrack, right? So having a relatively homogeneous surface is going to give me the easiest, or excuse me, the most accurate soil moisture estimates. And again, remember that when we're doing these deep learning models, we're only going to be able to predict as accurately as the data that we initially fed in. So I want to be able to give the model my best data possible. So that's why we chose this area of interest. Now I actually looked at a couple of different satellite data sets for soil moisture. On the left here, you can see the, I used the SMOS data set, which is from a European satellite, soil moisture ocean salinity from the ESA. And on the right, I have the SMAP satellite. Now, this black curve here in each of these plots is from one of these little yellow stations here. And these yellow circles represent observational or in situ soil moisture measurements. That's another reason that I chose this watershed, because as you can see, it tends to have a cluster of observational stations, which is not particularly typical, right? So to have a density of a monitoring network to be able to ground truth our experiments was really valuable to have in this sense. And so what I've done in these figures here, this black curve represents our observational or in situ data, and then the red and, or excuse me, the blue and red curves here represent the temporally synchronous soil moisture estimates from the SMOS and SMAP satellites respectively. And what you can see between these two data sets is that there tends to actually be higher variability and a dry bias with the SMOS data relative to the in situ data as opposed to the SMAP data and the in situ data. So the SMAP data actually looks like it has a better fit. And we did a little bit more analysis on that and looked at some of the distributions of our residuals. So typically, so when I talk about a residual, I'm talking about the difference, just the absolute difference between the SMAP soil moisture estimate and the observational data. So if you plot up a histogram of your residuals, if you could approximate a normal distribution over that histogram, we call that a robust distribution of residuals. And you can see that with the residuals from the SMAP comparison with our in situ data, we can actually approximate a somewhat normal distribution, whereas with the SMOS data, I hope I said SMAP over here, there are a lot of S's in this project, and I mix them up all the time. But with the SMOS data over here, you can actually see that there's a skew to the distribution that we fit over those residuals. And in some of these, this is obviously just for an individual station. With some of these stations, we actually see a multimodal distribution, which is absolutely not ideal. So I decided to use the SMAP data as my target. So again, here's a little picture of that network that we talked about before. Now I mentioned this, I think when I introduced the project that I'm working on, that SWOT accepts two different sort of data categories, right? So I have static data that describe the initial conditions of each of my grid cells, and then I also have dynamic weather data that changes throughout time at each of those spatial locations. So the interesting thing about that is that I was able to leverage a lot of success by processing those data types differently. And we can talk more about that in, I think, the next sessions. But what I did was I used a multi-layer perceptron, or that very simple network that we've been looking at today. I used a multi-layer perceptron to process the static data. So I have all of my data per grid point as my inputs, and I map that, of course, to my soil moistures that are spatially correlated with each of those model grid points, right? And I go through that in the same process that we've talked about before, the two-step training process. A forward propagation where I compute the loss, and backward propagation where I'm really minimizing that loss function. So I used another deep learning architecture to be able to process the dynamic data. This is a little bit more of an involved slide. This is maybe a more mathy slide to talk about LSTM. So let me talk about that in a cartoony type sense. So the architecture I use to process the dynamic data is called a long short-term memory network, or an LSTM. And really the important thing to think about that, so the overall structure of an LSTM, I'm not only passing input data from one layer to another in terms of steps across a latent space, but I'm also passing data from one time step to another. So I have another sort of, I guess, axis of activation, right, if you want to think of it that way. So I'm passing data not only through a latent space, but also through time. So I have a secondary dimension, and that's very important to think about. So when we think about soil moisture, one thing that I know about soil moisture is that the soil moisture today was really decided a week ago, right? The antecedent conditions are very informative as to what the physical processes governing soil moisture are going to output today. So the important thing about an LSTM is that we're really able to take those observations into historical context. Now let me talk a little bit about how that works. So what I have for an LSTM cell are two main components. One is in darker blue, is called the hidden state, or H sub t. And internal to the hidden state is what we call our internal hidden state, or C sub t, that I'm showing in this lighter blue color. So the hidden state is going to be the latent state representation at that node, at that time, given the input. The input that we're receiving into that hidden state are the values at time t, and the hidden state and internal hidden state, or memory, from our previous time step. So the important thing to note about the internal hidden state is really what we're doing is we're filtering through and storing important values in memory. And so what that means is that we're able to interpret the values from today within a historical context of which values have led to important predictions in the past. And we then output that, we use that historical context to inform the system state or the latent state at time t, and pass that on to the next time step and to the next layer. So this is a little bit more a complicated architecture that is able to leverage some of the important covariant trends that I have between particular dynamic parameters and my parameter of interest over time. So I've created, this is maybe actually a little bit out of date, but this is an overall sort of picture of what my network architecture looks like. And I call this a hybrid architecture because I'm using both LSTM and a multi-layer perceptron, or MLP, right? So initially what I was doing is I was taking my dynamic data and processing that through an LSTM. I was then taking the output activations from that LSTM and concatenating it with my static data and passing that through a series of MLPs. Now I'm just passing it through one MLP, so actually I should probably amend this figure a little bit. I was previously mapping to SWAT and then mapping from SWAT to SMAP, and I've now taken out this step of mapping to SWAT because it just made things quite a bit easier, and it turned out that it wasn't necessary. That's when I went from a surrogate to a pseudo-surrogate model, right? So again, the steps are process dynamic data,